Yeah, so all these patterns are basically based on the idea of high frequency patterns. Yeah, the kind of density-based notion we already mentioned, that we need to have a minimum number of trajectories come together in a region of a specific volume, and then some side constraints like at least k times, or there is a leader, or at least during a time interval and stuff like that. Yeah, so a kind of high frequency pattern. So something has to occur with high frequency, in that case in a given radius. Yeah, and that is the basic idea, that we have some kind of high frequency patterns. So beside these basic patterns proposed by Laube et al., I told you there are a lot of extensions. So the typical extensions are to propose something, some other criteria to be interesting, yeah, of interestingness actually. Yeah, so Laube et al., all the patterns of Laube et al., the interestingness of patterns of Laube et al. Are somehow constrained to a circular region, and the same speed and direction and stuff like that in a minimum entry. Okay, minimum entry is frequency, but the basic constraint of interestingness is this circular region here in these patterns. Yeah? And of course you can get rid of these circular regions. For example, you can look at paths or sequential patterns, instead of circular regions. Yeah, and that is what people very, very frequently also do. So look for frequently followed paths or frequent sequential patterns. Yeah, so what kind of patterns happen sequentially you have a sequence of coordinates of spatial locations. What are there any patterns that happen frequently in a sequential manner? Yeah, so sequential patterns that happen frequently. That is the basic idea. What is interesting in those things here? And of course, you can come up with many different things in that case here. Yeah? So we'll see in the following a little bit, or we'll detail a little bit about these followed paths, frequent sequential patterns. So we won't focus too much about these Laube patterns, but more about these frequent sequential patterns here. And one of the first approaches here to compute frequent sequential patterns was the paper by Cao in 05 here. And the basic idea here is to transform each trajectory in a line with several segments. I mean, if you look at this one here, the question is, how can you actually grasp this trend here of these different trajectories? I mean, they are not the same, but they somehow follow some higher order path, which is given here maybe by these blue arrows here. Maybe also here would be a good blue arrow, here would be a good blue arrow. So there seems to be a kind of prototype path that these trajectories follow, but of course they don't follow it perfectly. Yeah, and the question is, how can you somehow grasp these, or when do those different trajectories still follow a kind of prototype blueprint path, and when is it not the case? Yeah, and that is the basic idea of this paper here by Cao. So the idea is to transform each trajectory in a line with several segments. Yeah, so this is the original sequence, or the original trajectory, and we transform the trajectory into, or we get a coarser approximation into segments. Yeah, for that we need a distance tolerance measure, and all trajectory points inside this distance tolerance are summarized in one segment. Yeah, and we use, for example, here a distance tolerance measure of epsilon, and as long as all the observations of this trajectory are within this epsilon bandwidth, within this tolerance band of bandwidth epsilon, we aggregate them into one common segment, into one line here. So all these things here are within a bandwidth of epsilon, so we would summarize all those observations into one segment. Yeah, then similar segments can be grouped. Similarity is typically based on the angle and the spatial length here of the segment, and finally on a given distance threshold, and then we can group the segments according to this similarity measure, and each group is represented by a region around the medium segment. Yeah? And then frequent sequences of regions are just computed with respect to a minimum support threshold, because we can just get all these segments or sequences of segments of these regions here that have or that represent a minimum number of trajectories. So all clusters having a minimum number of trajectories are so to say reported. Yeah, so there is another work by Huang, also in the same year, that tries to compute frequent mobile group patterns. Yeah, so this is another kind of pattern. So it's a group pattern which is a set of trajectories close to each other with a distance less than a given minimum distance threshold for a minimum amount of time. So you need two thresholds, a distance threshold and a time threshold, and you want to find those sets of trajectories close to each other with respect to the distance threshold for for a given time, which is smaller, which should be more than the time threshold, obviously. Yeah? The direction in that case is not considered, so it could be, so here you see, here we have a trajectory going this way, a trajectory going this way. We don't care about that as long as the trajectories are within the distance threshold and during the same time. Yeah, so there's a minimum amount of time where this distance threshold is fulfilled. Yeah? And we can use the a priori algorithm here, or Huang proposed to use the a priori algorithm to compute those frequent groups. So we just have to apply this min-dist threshold and the min-time threshold to both domains, to the spatial domain and to the temporal domain, and then apply a priori algorithm. So here's a group pattern in that case, and you see once again that the direction of movement of the trajectories are not considered in that case. Yeah, then if you want to cluster trajectories, which is also very common, a paper by Han is maybe one of the pioneering approaches here, which proposed the so-called TRA-CLUS algorithm, which stands for trajectory clustering, obviously. Yeah, so it uses a density-based clustering algorithm, which is very similar to dbScan, to group sub-trajectories, and it uses a two-step approach here. So it partitions each trajectory in line segments with a user-defined length L, pretty much the same as here, but not with a distance threshold, but with a length threshold, so to say. We'll see that right in a minute. And then we cluster the similar line segments based on spatial proximity of the time points. Yeah? And a similarity of this, the line segments, the author proposes to just use Euclidean distance between the segments, but it could be anything else. For example, a measure that considers also time. So if you just take the Euclidean distance between the spatial information, you don't consider the time, but you could do that, of course. But here it's not considered, obviously, since it's just taking the Euclidean distance between the segments. So it's only considering the time, the spatial location.